welcome to the virtual science teacher. Today's topic is the operators on the quantum mechanics. What is an operator? Well, operator is a mathematical form to signify some physical parameters. In classical mechanics, particles are discrete and the problems can be solved by Newtonian mechanics. But in quantum mechanics, the particles are continuous, and as a result, we have to include the wave, and here operator plays a vital role to indicate the physical parameter. So operators are mathematical form of physical properties in quantum mechanics. So how can we deal with operator in mathematical form? Well, actually we have already known about matrix, and let us assume that A is a matrix, and we have already known that eigenvalue and the eigenfunction of the matrix. So if A is a matrix and psi is the eigenfunction, it operates on the matrix and produce some constant. This is eigenvalue, and remaining the eigenvector same or eigenfunction same. Here in quantum mechanics, A is called the operator, psi is known as the wave function, and lambda is the eigenvalue. The physical interpretation of eigenvalue in quantum mechanics is very important, but we will learn it later. Okay, so now what is some commutation relation? Let's begin with some operator. That is, we have some operator like two operators A and B. Okay, and the commutation of A and B, this can be written as AB minus BA. Okay, you have already dealt it in matrix, and in this case also similar like matrix form. AB not equals to BA. That means product of A with B and product of B with A are not same. These two operators A and B are called commute. That means AB commute itself if AB equals to 0. That means AB minus BA equals to 0. That means if AB and BA equals, that means A multiplied with B and B multiplied with A provides the same result, then A and B operators commute itself. Okay, so now let's see what happens for three operators. Suppose we have to deal with some operators like A, B, C, or A, B, C, this type of operator. So how can we deal with it? Actually, this is nothing but some simplification form of this sum. We have to simplify by using this equation. So I am writing it as A, B, C minus BCA. Here we can think that BC is a operator, and we are trying to commute with A and B, and now I want to subtract some operator. Okay, so actually I am subtracting now BAC from this term. So I have to add BAC to make the quantity same. BAC minus BC. Okay, so let's see what happens. From these two terms we can common at right side C. So what happens, remains as AB minus BA. This will give us at AB, because AB minus BA provides us AB, and C plus, from this term B can be common out at the left side. This will provide us AC. Here is some important technical notes. You have to remember this. that if there is an operator at right side, you have to deal it at right side. You can't do it without any commutation to the left side. Okay, or otherwise, if there is an operator at left side, you have to deal it at left side only. You can't take the left side operator to the right side. Okay, so whatever. So what happens for a comma b, we see this type of operator. In this case, b comes out at the left side, ac commutes, and then c comes out to the right side and ab commutes. Okay, so if you have to deal with this type of operators, don't confuse, just observe the operators first. Put the first operator before the commutation and last operator after the commutation. Okay, so now let's find some operators of the physical parameters like linear momentum, angular momentum, kinetic energy, total energy, etc., etc. Okay, so first deal with linear momentum and energy operator. We have already know about the wave function. The general form of wave function is psi xt. Okay, psi is the wave function, x is the position, and t is the time. This can be written as a e to the power I kx minus omega t, where k is the propagation factor and omega is the frequency by which wave is propagating. Okay, now let's see what happens for linear momentum case. Actually, we are doing now some differentiation with respect to x. So what happens if we differentiation with respect to x? It will provide us ik a e to the power I kx minus omega t. That means we can say that ik psi. So what about k? Actually, from the equation of the Broglie, p equals to h by lambda, and we can write this by this. We know that 2 pi by lambda is, what is 2 pi by lambda? 2 pi by lambda is the propagation factor, that means k. So we can replace k instead of 2 pi by lambda, and h by 2 pi is known as h cut k. K is replaced by 2 pi by lambda and h cut is replaced by h by 2 pi. In quantum mechanics, in maximum time, the equation are deal with h cut, not h by 2 pi. These are same. Okay, these are just conversion. So I can write here p by h cut instead of k. So what happens? I p by h cut psi. So rather than it will be, so what happens for p psi? P psi equals to minus I h cut del psi del x, because 1 by I equals to minus I, that is why I am writing this minus I. So now comparing to the first equation, that is here p is something which is operated on a wave function psi and produces something remaining the wave function same. That means we can write that p equals to minus I h cut del x. So we have found that p equals to minus I h cut del x. This is along x axis, that is why I can write that p of x okay, one of the basic operator, linear momentum operator. So what happens for three-dimensional case? That means if we have a operator in 3D case, so actually in general what happens, P equals to pxi pyj pzk, that means px I unit vector plus py j unit vector plus pz into k unit vector. That means I, j, k are the unit vectors along corresponding axis, and px are the angular momentum. Sorry, px is the linear momentum along x-axis, py is the linear momentum along y-axis, and pz is the linear momentum along z-axis. So in general, what I can write? I can write that I h cut. This I is iota. That means root over -1, and this I is unit vector. Remember this. I having hat at the top is unit vector. I is cut del x I unit vector plus j unit vector del y plus k unit vector del z. So we can write I h cut grad. This is the linear momentum operator in 3D case. Okay. So now going to the energy operator. Again we are starting with wave function psi. Wave function psi equals to a e to the power I kx minus omega t. Now I am differentiating it with respect to del t, that means with respect to time. So what will give us? Minus I omega a e to the power I kx minus omega t. So now what happens for energy? Energy equals to E equals to h nu, where h is the Planck constant and nu is the frequency. So h by 2 pi into 2 pi nu, where h is by 2 pi indicates the Planck h cut said earlier, and 2 pi nu is the angular frequency, that means omega. So in this case I can write that del psi del t equals to minus I omega psi, otherwise this can be written as this can be written as I e by h cut omega instead of omega. So e can be written as I h cut del t. So total energy can be written as I h cut del t. Okay, this is the total energy. Well, so what happens for kinetic energy? What is kinetic energy here? Kinetic energy we have written as kinetic energy by K is the kinetic energy. Okay, kinetic energy can be written as P square by 2m. So we can write that P square equals to minus I, P equals to minus I h cut grad, that means minus I h cut whole square 1 by 2m into grad square equals to minus h cut square by 2m grad square. That means kinetic energy provides us minus h cut square by 2m grad square. This is the basic kinetic energy operator. Okay, so what happens for Hamiltonian operator? What is Hamiltonian? Hamiltonian is kinetic energy plus potential energy. Okay, so in one dimensional case, kinetic energy equals to minus h cut square by 2m del 2 del x2 plus v of x. This is simple the Hamiltonian of a system in one dimensional case. For three dimensional case, for what happens? H equals to minus h cut square by 2m grad square plus v over. Okay, so what we have found is h equals to p square. This is the basic Hamiltonian. Okay, now coming to the angular momentum operator. So what we know from classical mechanics, that what is the relation between the angular momentum and the linear momentum and the position. Well, suppose L is the angular momentum, R is the position vector, and P is the linear momentum. So the relation between these three major physical parameters in classical mechanics is L equals to R cross P. That is the cross product of R and P. R is the, where R is the position operator. This can be written as x into x unit vector plus y into y unit vector plus z into z unit vector. You hats over the x, y, z. This indicates the unit vector corresponding to the corresponding axis. Okay, and what happens for P also? P can be written as px x unit vector plus py y unit vector plus pz into z unit vector. Now in quantum mechanics, we have already defined the linear momentum operator. That means P has been defined as minus I h cut grad. That means this is x unit vector del del x plus y unit vector del del y plus z unit vector del del z. Okay, so I am just putting this R and this P here. Okay, so what happens, and finding the cross product value. So for cross product, I can write this by this method. This is x, this is y, this is z. This is minus I is cut. For all case, I can take the minus I is cut at outside of the cross product to write less. Okay, now L can also be written as Lx into x unit vector, Ly into L unit vector, Lz into z unit vector. I am just doing nothing, performing this determinant and comparing with the unit vectors of both sides. That means equation 1 and equation 2. Okay, so this will gives us at Lx equals to minus I is cut y del del z minus z del del y. I am not performing here the determinant, because I think you already know how to solve the determinant. Well, so what happens for Ly? Ly equals to minus I is cut z del del x minus x del del y, sorry, x del del z, and Lz equals to minus I h cut x del del y minus y del del x. Okay, so these are the three components of the angular momentum operator. Nothing about the linear angular momentum operator, because just perform this determinant and compare both sides with the unit vectors, then your process is half done. We have represented the angular momentum in operator form in code in Cartesian coordinate system. So in sometimes we have to deal again in polar form. So what happens of the angular momentum operators if we have to deal with operators in polar form? Well, so let's check. In the coordinate system, what we know is this, that x is the angular momentum operator, x is the x-axis, these are the z-axis. So I think P is a point where a particle is remaining, and the distance from the origin to the point P is r. The angle between z-axis and this plane, OP plane, is theta. And now I am drawing some projection on xy plane from point P. Okay, this is suppose Q, and I am joining a line from origin to Q, which gives us the angle between the x-axis and the OQ is phi. So from this term we can write that z equals to r cos theta, x equals to r sin theta cos phi, y equals to r sin theta sin phi. These are the basic conversion relation from Cartesian coordinate system to polar coordinate system. Okay, so now let's check what happens in polar coordinate system. So we have the relation of x equals to r sin theta cos phi, y equals to r sin theta sin phi, z equals to r cos theta. These are the basic relation between r theta, Cartesian coordinate system, and the polar coordinate system. So what happens if I want to write r theta phi in terms of x, y, z? R equals to x square plus y square plus z square, theta equals to tan inverse square root of x square plus y square by z, phi equals to tan inverse y by x. Okay, these are the relation of r theta phi in terms of x, y, and z. Now we have to use the chain rule in partial differential equation. Let's say chi is a wave function of r, theta, and phi, and r is the function of fx. Similarly, theta is the function of fx, and phi is also a function of fx. Then if we want to find out the differentiation of chi with respect to x, this will gives us a del chi del r into del r del x del chi del theta into del theta del x, del chi del phi into del phi del x. That means I can write that del x equals to del r del x into del r plus del theta del x into del theta plus del phi del x into del phi. Similarly, I can write del y equals to del r del y del r, del theta del y del theta, del phi del y del phi, and del z equals to del r del z into del r, del theta del z into del theta, del phi del z into del phi. So these are the basic equation for the conversion from one state to another. Then our main job is to find these terms related with del r del x, del theta del x, like this. So let's check what happens. Actually, del r, now I am finding del r del x. This will gives us at x by r equals to x by r equals to sine theta cos phi del r del y equals to y by r equals to sine theta sine phi, and del r del z will provide us z by r equals to. So our next job is to find the partial differentiation of theta with respect to x, y and z. So let's see first what happens for del theta del x. Okay, del theta del x equals to what? So we know theta equals to tan inverse square root of x square plus y square by z. So del theta del x will provide us that means we have to differentiation theta with respect to x, and what is the differentiation of tan inverse x with respect to x? That is 1 by 1 plus x square. So I am doing the differentiation here, 1 by 1 plus x square plus y square by z square into 2x by square root of x square plus y square. Z will comes out to the outside, so it will remains as z square. This z square will goes to the upward, that means numerator, and there is one z at denominator, so one z remains at numerator. Now I am putting the values of x equals to r sin theta cos phi, y equals to r sin theta sin phi, and z equals to r cos theta, which will gives us 1 by r cos theta cos phi. That means del theta del x provides us 1 by r cos theta cos phi. Similarly, if we try to find out del theta del y, this will gives us 1 by r sin phi cos theta, 1 by r sin phi cos theta. Okay, and cos theta cos z will provide us minus 1 by r sin theta. Now I am interested to find the values of del phi del x, that means the differentiation of phi with respect to x, y and z respectively. So now what happens for phi? Phi equals to tan inverse y by x so del phi del x provides us minus 1 by r sin phi by sin theta. Del phi del y will provide us 1 by r cos phi by sin theta, and del phi del z provides us 0. Now our main job is to find out Lx, Ly, Lz in terms of r theta phi. That means Lx must be written as a function of r theta phi, Ly must be written as a function of r theta phi, and Lz. So putting these values, we can simply write that Lx equals to minus I h cut. Just put the values of del theta del x, del r del x, and so on, and put the values of Lx in the form of Cartesian coordinate system. So this will gives us at minus sin phi del theta minus cot theta cos phi del phi, cot theta cos phi del phi. Okay, I have to just participate these. Next, what can we write? Ly. Ly equals to minus I h cut cos phi del theta minus sin phi cot theta del phi. These are almost similar. Lx and Ly are almost similar. Lz equals to minus I h cut del phi. Okay. So these are the form of angular momentum operator in polar coordinate system. We have already discussed the linear momentum operator, angular momentum operator, kinetic energy, total energy, etc., etc. These physical terms are very important even in quantum mechanics. Now there are two more operators in angular momentum operator. These are called step-up operator and step-down operator. So mathematically, what we can say? Mathematically, step-up operator is written as L plus, this is as Lx plus I Ly, where I is the square root of minus 1 and Lx, Ly are the angular momentum operator along x-axis and y-axis respectively, and L minus is called Lx minus I Ly. This is called step-down operator. Why these names? Actually, we will see later that when a step-up operator operates on a wave function, its states will increase by a factor 1, and when step-down operators operates on wave function, its states will be decreased by a factor 1. So don't worry about this now, but just remember this, that step-up operator is defined by L plus, and this is as Lx plus I Ly, and step-down operator is given by L minus. This is mathematically written as Lx minus Ly. More will be discussed in the next class, and for more enquiry, please mail us at versiteach@gmail.com. Also, please subscribe our channel for further updates. Thank you.